an answer to the statement.
Yes, the answer is that the
discussion
inconsistency that you referred to is the inconsistency with the standard lambda CDM model that you're talking about. And indeed, in the framework of that model, if you make corrections and then you find them to be consistent with the model you have assumed, that is as it should be, because you are doing the exercise quite carefully. What I'm saying is that if you actually look at the measurements that were made, and given the statement that whether you use heliocentric redshifts or local group redshifts or CMB centered redshifts, that from the point of view of general relativity, there is none of these has a special status compared to any other. You must take into account that there should be a invariance principle that governs how the universe looks. And you cannot demand to only observe it in the privileged, singular, maximally isotropic and homogeneous, maximally symmetric frame that is the FLRW universe. So what you are saying is that everything fits together very nicely if I assume FLRW and everything matches. That may be true, but it leads me to this conclusion, leads everyone to the conclusion that the universe is dominated by a mysterious cosmological constant with a scale set by the present-day Hubble parameter. And as a theoretical physicist, I consider that to be absolute nonsense. And therefore, I would like to look at the data to see what assumptions have been made to come to that conclusion. And the primary assumption seems to be that of that the CMB frame is the correct frame. And I've given you an empirical evidence that that ain't so.
Okay.
So as an observer, I'm sure you'd be interested in pursuing that.
Okay,
Let's go. You'll have to talk later. I'm eating into Dan's time
we
now.
have a discussion session next. So let's listen to Dan so that everybody can profit. And then for the discussion, we can go back to all of these fascinating things. Please, Dan.
Great. Okay. Can people see my slides? Okay. Yes. Great.
Yes.
All right. So first, thanks to the organizers for having me. I kind of have a lot to do today. As I know a number of you have seen, there's this big paper that came out in the archive last night that tried to explain away the entire Hubble constant tension. So I quickly kind of added a bunch of slides for this talk about that. They'll come in later. So I'm going to kind of blaze through a bunch of things, and I hope you'll forgive me. So this will go a little bit fast, but I'll try to get to everything. Okay. So just a quick primer for how type 1a supernovae work, because that's kind of the main focus of what I'll talk about, is that we know the intrinsic luminosity at about 10%. You can measure the apparent luminosity after you do these standardizations that there's a lot of work on. The ratio of the two gives you a luminosity distance. Then independently, you get a redshift either from the supernova or the host. And then for every supernova, you can put the distance modulus and the redshift on a Hubble diagram, and then you can measure cosmology. Okay, now over 20 years ago now that this is kind of the big discovery of the accelerating universe, you can see this plot on the left. This is with tens of supernovae. Kind of the big sample that I worked on is called the Pantheon sample, and that's what you see in the middle. So we've gone from tens to now over 1,000. And you could see in omega lambda, omega matter space, the contours in black, that's kind of from the discovery sample. And then in red, that's what we have now. And you can see kind of a very strong significance of omega lambda greater than 0. And kind of there's a lot of work that went into this that I'll skip over, and let's talk about a couple different things. Okay, so to say that what we find is acceleration consistent with the cosmological constant, W equals minus 1.026 plus or minus 0.041. But say that we have kind of very weak constraint on W sub A. So any kind of evolution, that's where we're not there yet. And I think kind of the next round of telescopes like LSST, Roman, that's where we'll really nail that down. Okay, now a number of papers kind of looked at Pantheon and combined Pantheon with other results and tried to say, could dark energy be something weird or different? The short answer is nothing's screaming out. So on the left, this is a paper I worked on with Suhail Dewan, Dylan Brown, and others. And you can see, there's some deviations on the kind of couple % level. A lot of this can be explained by systematics. but kind of nothing that pushes you significantly to any other kind of dark energy model. And I think kind of in response to the last talk, it's really important to realize that supernovae are not the only evidence for dark energy. So this is a nice plot from Nandathar et al. That came out last year that shows voids and then Pantheon supernovae, BAO, and then from CMB. And you see this kind of beautiful concordance picture of where omega lambda sits, and you can see here in the caption, this is greater than 10 sigma detection acceleration. So, if supernovae have all the problems, that would be terrible for me, but dark energy is still quite significant. Okay, okay, and I'll say one thing that I try telling people is like, so like I'll put out this Pantheon set, and people kind of just take distances or do one of their own things, and we spend a ton of time basically creating these kind of particle physics like four model simulations of our sample, where you know what your weather history and what happened during every observation, and this way you can model all your selection effects and noise properties and everything. And we do all sorts of validation for this forward modeling, and then we use that to do our cosmology analysis. And we produce these realistic simulations along with our data set. So if anyone wants to go and take Pantheon and say there's something very strange with the universe going on, my biggest ask has always been, well, just validate it on a simulated sample, so you can be sure that you're not introducing something new that shouldn't be there. And kind of my message hasn't got across super well, but I like to always say this. Okay, now, so that was a few years ago, and what I have been working really hard on is what's now called Pantheon Plus. And basically this is kind of a combined analysis with the next big shoes paper. So Alicia has talked about shoes, and I'll talk about that later in the talk, but basically a lot of the community has asked for all the covariance between the calibrator supernova used to measure the Hubble constant and the supernova used to measure W to be combined together. And so you can see a pretty zoomed out version of kind of where we are now. So this is not released, but the hope is we're writing right now. And mu model in this case is your totally vanilla lambda CDM. So there's nothing in this kind of zoomed out version, there's nothing very strange going on. And I want to say, like, even if there's something locally where it's just some weird part of the universe, fine, you could cut off our redshift distribution at z of 0.1 or z of 0.2, and you still get a significant detection of dark energy, and the model agrees. So even if you try to say, yeah, we're totally in this kind of weird place, and you just want to get out of there, we now have enough data to still strongly favor dark energy. Okay, so there's been a number of papers that talk about supernova systematics, and I want to talk about them kind of in kind of what Subir just talked about, but also kind of in the thinking of H0. And kind of one thing that's come up a lot is that a lot of the focus is on the distances of supernovae, but we care about the redshifts too. And then the other thing is what's the relation between supernova properties and their host galaxies? Okay, so with regards to Subir's talk, I'll just kind of echo what Mike Hudson has said, that, there's a number of papers that just aren't really seeing the same thing. There's this nice paper that just came out, I think last week, Stahl et al., which finds consistent measurements with using 2n++ with lambda CDM. And yeah, and kind of what I was saying before is that we're seeing less and less room for some deviation from lambda CDM with supernovae. And I am totally happy to give people early looks at Pantheon Plus as long as we have some like publication embargo. But going from 1,000 supernovae to 1,700 supernovae, and especially increasing the low Z sample makes a huge deal for this. So that's all I'll kind of say about that. But there's also been issues pointed out about, okay, some of the redshifts have been updated, and what's the right peculiar velocity treatment to do. So Anthony Carr, who's Tamara Davis's grad student, he's kind of done a full sweep of kind of where all the redshifts come from and making sure the right host galaxy is picked and checking every catalog. And basically, there's extremely little difference in your final cosmology if you do that. And then my student, Eric Peterson, he's doing kind of a consensus sweep of different peculiar velocity treatments. And he sees that you can move H0 around due to peculiar velocity treatments on the level of 0.5, which is still significantly less than the tension. But if you kind of just look at which ones are actually helping the data, like the ones that Mike Hudson work on, those are much better constrained to like 0.2 in H0. Okay, all right, so what I want to get to is this kind of really interesting thing about dust. And this is going to relate to the paper last night, but I'm going to have to kind of go through supernova to tell this story. All right, so one of the big things I worked on in the last year is trying to explain 3 key mysteries of type 1a supernovae, which is that when you do the standardization and you subtract out your best fit cosmology, the Hubble residuals will correlate kind of weakly, but it's there with properties of the host galaxy, and no one has known why. Second is that after you do the standardization, there's still some leftover what we call intrinsic scatter of the residuals. And what does that do to? And 3, how does the supernova color relate to supernova luminosity? It's kind of been found that it seems like supernova color doesn't really look like dust and what's going on. Okay, so kind of point 1 is that we do this standardization, you subtract out the best fit cosmology, and basically all I want you to see here is that kind of right around 10, right around your kind of middle mass of your host galaxies, there's a bit of a step. So this is called the mass step, and it's been this big question in the SN1A community. And kind of one of the leading ideas for a little while was like maybe somehow you have progenitors of supernovae more likely to be in certain kinds of galaxies, and the progenitor explosions will be different. So that was popular for a little while. So this is like, maybe some of you have heard this Mikhail Vergo idea, where they see the significance. This doesn't really change H not much or W much, but this kind of was the popular thing for a little while, but it just kind of wasn't helping that much. It just kind of seemed to be there, and it doesn't answer any other problems. Okay, so then the second thing is that if I look at these Hubble residuals, so each point is what we call a Hubble residual, there's just some scatter, and it cannot be fully explained by measurement noise. And so the question is, well, what's causing that? What's different between supernovae? Is it the explosions themselves? Is it something around the supernovae? We don't know. And then the kind of third question is, what's going on with supernova color? Because when people try to do any kind of inferences of supernova dust, it looks like the R/V, the kind of reddening ratio, which is typically 3.1 in the Milky Way, we're not seeing that for supernovae. So for some reason, it looks like dust around supernovae is not like dust in our own galaxy. And this is kind of foreshadowing for the paper that came out last night. My big point is that in some sense, this is new astrophysics. So we're saying, we don't know why, but just it seems like dust kind of around or in the galaxies of all other supernovae in any other galaxy just doesn't look like dust in the Milky Way or the LMC or any kind of really nearby galaxy that we could look at well. Okay, so what Dylan Brown and I put forward is that all of these mysteries can be explained with the idea that supernova color can be explained by dust, and the properties of dust vary depending on the type of galaxy, or basically the mass of the galaxy. So using this kind of 1700 supernova compilation, we see these extremely strong effects, 11 sigma, 8 sigma. I won't go into there. But basically what they're showing is that the scatter of the Hubble residuals, what you see here in the middle panel, increases as your supernovae get redder. And really the only way you could do this is if you have some kind of variation of your dust law. So we build this model where we say, okay, there's some intrinsic component. So on the left here, this is the intrinsic component. And then you have some extrinsic dust component to the color that you see of supernovae. And then basically what we see is the combination of the two. And this is still all with regards to supernovae. The paper that came out last night was with regards to Cepheids, and I'm going to get to there, but it's like surprisingly similar. So that's why I'm doing this. It's just very topical. And what we're saying is that dust is weird and it has a lot of RV variations. That's why you get this scattered to go up as your supernovae get redder. Now, what came out of this, kind of almost like this just came to surprise to us, is that this could also explain the mass step. Basically, the data set wants there to be that the type of dust or kind of the reddening ratio is different for high mass hosts than low mass hosts. And what that should predict is that this step that you see on the bottom left here will increase as your supernovae get redder. That's exactly what we see in the data. So the green is our prediction, the black is our data. We can predict this kind of total mystery that people haven't been able to understand. Now, this causes a 4% bias in W. It doesn't remove the need for W, but this is what I would call our largest systematic. So kind of this is not an existential threat to W. It's a serious systematic because it's kind of combining all the top issues with type 1a supernovae. Okay, so kind of to answer these questions, why does it appear that publishers correlate with properties of the host galaxies of type 1a supernovae? Well, we're saying it's different dust laws for different types of galaxies. What's the intrinsic scatter due to? We're saying variation of dust laws. And how does the supernova color relate to the supernova luminosity? We're saying that it's mostly dust, but this dust is not like Milky Way dust. And one prediction that came out of this is that, okay, if we're saying everything is dust, then in the near infrared, well, you're less sensitive to dust. So you can see through the dust more. So if people go and try to measure the mass step in the near infrared, whether or not they see it will confirm or deny whether Dylan and I are right or not. Okay, so basically over the last year, there have been a few papers that have come out taking these really small samples since it's hard to get near infrared measurements. And they say we see the same step in the near infrared as in the optical. So takeaway point here is just they see the same step. So therefore, kind of what I was saying is incorrect. But you could kind of just see by eye, if you look at these points, you have many 10 sigma outliers. So the analysis here is challenging. So then just a couple of weeks ago, this team, this is kind of a lot of Ariel Gubar's group, who is the same team that put out the paper last night. So this is kind of all very, I don't know, together. They compiled a huge sample of supernovae in the near infrared. And they say, oh, yes, there is a huge amount of R sub V variation, and it doesn't look like Milky Way dust. And basically, they confirm what the Brown and Scolnic paper said. And you can see this on the right here, that you have this kind of big step in the optical. And as you get more into the near infrared, it goes away. And if you just let R sub V float, if you say there could be a different R sub V for every galaxy, that's another way to get it to go away, which is what our paper predicted. So this made me feel really great that, okay, dust in our galaxy or the very nearby galaxies is just weird compared to the other galaxies that have supernovae, but this explains a lot of the mysteries of supernovae. Okay, and I'll just quickly say, just to tie up the supernova part, that supernovae can be used with Cepheids. They could be used with baryon acoustic oscillations or strong lens systems. And generally, they play the role as the middleman. It's kind of, they could give you high or low H0. So it'd be very hard for supernovae to be somehow busted, considering they kind of are doing the delivery for any of the other probes. And I'll also just kind of say to that point that you could replace supernovae in the distance ladder to measure H0, and you get roughly the same Hubble constant. So you could use surface brightness fluctuations or different types of supernovae, not type 1a, and you get roughly the same H0. So in my mind, the kind of the supernova part is pretty robust. Okay, so we've talked about, so now I'm transitioning to the more the H0 part, how kind of there's this very interesting tension, and why doesn't kind of the measurement of the universe from the CMB match up with what we have today? All right, and a lot of you have seen these various what's called the whisker plots. There's a lot of arguments going on about what's the right way to make it. Either you could say there's super tension, or you could say we're all meeting in the middle. This depends on the user. Okay, so just skipping over, this is the normal 3 steps. We've talked about this. And there's even kind of some tension within the tension. So kind of on the local side, there's tip of the red giant branch measurements, and they have a 0.06 mag offset compared to Cepheids. So kind of totally forget about the supernova part of the distance ladder, but there's some disagreements and there's been a lot of back and forth in the literature. I'll say the TRGB also kind of have their own dust sensitivities, and that's been pointed out, but this is ongoing of kind of Cepheids versus TRGB. Where does this land? Both of these are still kind of higher H0, but the question is how high H0? Okay. So one thing that's been a big boon for the SHOES team is just being able to use Gaia. And I'll just kind of say this is Gaia DR2, then this is Gaia DR3. So kind of if you trust Gaia, you get a high value of the Hubble constant, assuming no other systematics. But now there's been some discussion about what are the systematics in Gaia. And then there's been a lot of focus on kind of what are the Cepheid systematics, and this is what I want to get to. Can I just ask how much time I have? Okay.
10 minutes.
10 minutes. Okay, great. I can do this in 10 minutes. Okay, so there's been a few questions, and I want to get to the thing from last night because that's not the most exciting. Okay, so just blazing through the issues. One that's been pointing out is that Cepheids are near other stars. They get blended in. There's this nice paper by Adam Rees, 2020, that kind of shows that we can predict that exactly and model that very well. That doesn't seem to be the problem. There's another issue that's been pointed out, which is that maybe just the photometry could be done wrong, this difficult photometry. So this other team led by John and Marty et al., they take the kind of raw images and do everything themselves, basically try to make different choices, and they get a similar value of the Hubble constant. So it doesn't seem to be the kind of actual measurement itself. So the last possibility is what if something going on with kind of Cepheid physics? And this is kind of where now we're tied into what went down last night. So this is a plot of what's called the Hertzsprung progression. So this is just the magnitude versus phase. And on the top panel, this is showing in type 1a supernova hosts, and the bottom panel, this is showing in Milky Way hosts. And the key for doing the distance ladder is you're assuming that the physics of Cepheids is the same in the Milky Way, or kind of your where you can measure some geometric anchor compared to the supernovae hosts. And if you look at these, you see the same fundamental asymmetry bump to 1 resonance modes, all these same modes. Everything looks very similar between the Cepheids and the supernova hosts and the Milky Way hosts. Okay, now this paper came out last night that said that you can explain away the Hubble tension because of due to dust. And the thing I want to point out is that there's two numbers in the abstract, and they're actually doing very different things. So you can see here, one number is taking these Weisenheit magnitudes, and I'm going to explain what that is. And doing it this way, you get an H0 of 67. And then if you do this other way, where you're measuring the color excesses compared to intrinsic colors, then you get a high value of H0, maybe moves down a little bit. Now, the claim I want to make is that this first way is really changing the physics of Cepheids, and this second way is modifying assumptions about the dust of supernovae, basically doing similar things to what I talked about for supernovae. So the title to me is actually quite misleading. It's not the dust that's changing H0, it's the physics. The dust itself is keeping you with a high value of the Hubble constant. So let me try to back that up. And I've only had like 12 hours with this paper. Okay. All right. So the idea for the distance ladder is that Cepheids around us, so that's in the Milky Way, LMC, M31, NGC 4258, all within 8 megaparsecs, are the same as Cepheids in the supernova host, which are between 7 and 50 megaparsecs. So basically, you're saying these have the same colors, same magnitudes for a given period, and this is kind of essentially relying on like the Copernican principle, that there's nothing that special, nothing crazy that happens right around 8 megaparsecs where Cepheids will suddenly change. So when they measure the distance. So this is kind of thinking of things from a dust perspective. Basically, there's two components. There is, sorry, this is a little messy. I just did this morning. There is a correction for the intrinsic color of the Cepheids, and then there's another correction for the excess dust of the star. So in the paper, the two different ways are basically saying, all right, in way one, we're just going to say, hey, the differences between Cepheid colors is due to dust. So let's just kind of multiply that by the Renning ratio for dust. But then they have this other way where they say, hey, let's just kind of glob all the color of Cepheids together, and we're just kind of like a single Weisenheit ratio that we're gonna multiply the color for. Now, if you do it this first way, which I think is the kind of much more prudent way, it's kind of much more similar to what I talked about for supernovae. You say, all right, there's some differences between Cepheids due to dust. You could see that this R sub E, this reddening ratio is lower compared to the Milky Way. To me, actually, I quite like that because that's kind of similar to what we see for supernovae. And if you do that, you get a value of the Hubble constant of roughly 72. So a little bit lower than Shoes, but this is not such a big deal. Okay, now if you instead say, hey, Cepheids just can be very different physically. This is not dust. This is just the physics of Cepheids. For things less than 8 megaparsecs and things more than 8 megaparsecs, and you just kind of let this kind of fairly unconstrained parameter go. So you see here, this is R sub W versus galaxy. So you're essentially adding 25 free parameters here. And the point that you could see is that kind of for these nearby galaxies, they prefer this higher value of R sub W than galaxies kind of beyond 8 megaparsecs in our second rung of the distance ladder. So if you say somehow the physics has changed in these Cepheids, then you could get this low value of the Hubble constant. But basically, if you're going that far, you're saying like that Cepheids, the kind of normal, like kind of how hot you are compared to how bright you are, doesn't work anymore. You're saying things that are cooler are not fainter. This R gets close to 0. So somehow you are totally changing stellar astrophysics, and that's not dust. This is kind of I think a very I don't know the word for it, big claim for how to change astrophysics. Okay, so did the H0 tension go?
5 minutes done.
Oh, okay, yeah, I'm just about done.
Yeah.
Okay, so did the H0 tension go away last night? Okay, so I say they brought up two possibilities. So one is we may have discovered that galaxies have very different dust than the Milky Way and other kind of very nearby galaxies. So I think that's actually quite neat. That would mean that supernovae, what's going on around supernovae isn't something that special, but you still have the H0 tension and it didn't go away. The other possibility is that for some reason, the physics of Cepheids should change right around 8 megaparsecs. There's no other evidence to support this, and it's I think a much tougher leg to stand on, except that this can get rid of the H tension. So I mean, I personally think this possibility 1 is much more grounded. Possibly 2, kind of I never really saw or heard before. Either of them really are kind of saying new physics, but just this is more astrophysics than cosmology. And I think people have been looking at cosmology. So if I would feel great about possibility 1, possibly 2, I would need a lot of more convincing, because that just feels like pulling a big one. But yeah, I guess more time will tell. Okay, so lastly, I'll just say, all right, let's go back to this idea that maybe it is real. So we've kind of heard about this. One of the things I think that has been so difficult is there just hasn't been a good theory to explain everything. So there's been theories that can move H naught around, but then you'll break something else. And I think kind of one thing we've been fighting against is never believe an experiment where there's not a good theory for. And I think we're still in that scenario. So everyone should be looking at every place, whether it's new astrophysics or new models, and more time will tell. So I'll leave it there and happy to take any questions.
Thank you very much. So open for questions now. I can ask a simple one. Okay, Elias, yes. Elias, you're muted.
Sorry, I have a very naive question. Do we understand in detail the physics of the Cepheids?
Yes, great question. So in some sense, these are empirical, like we're using them empirically, just like we use type 1a supernovae empirically. So there are some limits of how well we understand them, but at least compared to supernovae, they are well understood. Like the reason that they have these different overtones is well understood. So there will be people that say there's still things that we don't know about Cepheids, which I think is true. But for kind of empirical objects, I'd say we understand them well enough.
Well, you mean that we have observed, of course, them for a long time and we have lots of data. But the question is, do we understand the mechanisms that drive the Cepheids?
Yeah, I would say many of them, but the picture is not complete.
I see.
Yes. It's a much better scenario than we are for type 1a supernovae in terms of understanding the mechanisms, but it's still not quite there.
Thank you.
I had the same question for supernovae 1a. There is much simulation for core collapse supernovae type 2.
Yeah.
But is there simulation work going on for 1a? It is fusion explosions, but is there simulations to learn from?
Right, great question. Yeah, so there is. I was a lot more tied into this a little bit time ago. So basically, there's a number of simulations that try to work out the explosions of type 1a supernovae. The issue that I have always seen is that the simulations can't predict how amazingly well supernovae can be standardized. So basically, empirical supernovae look way more kind of standard than simulations would say they should be.
Yeah, this is
and that's always been a big surprise, and simulations aren't there yet.
Okay. Nyayesh?
Thank you very much, Dan, for the excellent talk on such short notice on this topic. So a question for you, why dust being different in other galaxies is okay, but Cepheids being different is not? I mean, why one is better than the other from astrophysics?
Right, yeah, great. That's a great question too. So we've seen, we've seen that, it's a great question. I don't know. I really like that question. To me, I'm almost excited about both of them. Like, there's some saying which is like you're only allowed one like crazy idea per paper or whatever. So I think
one tooth fairy, that's what we call it. One tooth
fairy. That's right.
Thank you.
I was trying to remember that thing this whole morning. What's the expression? Yeah, one tooth fairy. So this feels like we're getting into two tooth fairy land. Right, we have seen other galaxies have different Rs of V's. Like the LMC has a much higher Rs of V. So we have seen it happen, but like when I talk to the dust experts, like Doug Finkelstein, people like that, and I say, hey, supernovae, we see these really low Rs of V, they would say that sounds very unlikely. I'm not sure how you can make that. And the kind of only kind of exciting work on that front has been like, oh, maybe around supernovae, there's a lot of crazy things happening. So the environment is just so weird, you get these weird dust things. But now if it turns out Cepheids also show these very low Rs of V's, then there's just kind of some kind of fundamental misunderstanding of how dust works. I guess there's not that big of a gap between that and Cepheids being very different. I think for the dust thing, at least there's other people that have said, hey, dust can be weird. People before haven't said, hey, Cepheids should just suddenly change around 8 megaparsecs in how their physics works. And for some reason, when they're cooler, they stop being fainter. Like no one has said that before. So that's quite a big tooth fairy.
Couldn't that be like metallicity dependent somehow? These ones are different metallicities from Milky Way?
Yeah. So that's the metallicity thing. It has been looked at well now, and so that's marginalized over, fitted in different ways, and that doesn't have much of an impact. So yeah. So I say this here in this slide, but whatever metallicity dependence has kind of already been taken into account and doesn't change suddenly at 8 megaparsecs. So somehow, yeah, I don't know the kind of thing that can do this, that just makes these Cepheids, basically you're saying they're not even Cepheids anymore once you get far enough out. So you're really kind of taking down the whole idea.
Okay, thank you.
Are there other questions, Norma?
Very shortly. Thank you very much, Dan, for this. I found a great talk. Perhaps going in about the last question and going in the direction to explain why one possibility better than another. I mean, you take dust, I agree with you. Perhaps it's just from the physical point of view, the fact of generality is much more said acceptable with all the observations and all that does change with in the different galaxy types and population, and not all galaxies and dust around must be equal to the as in the Milky Way. Mm-hmm. And that is rather, I mean, from the physical point of view is rather acceptable, while just looking at one, I mean, just a Cepheid and putting on just saying that is needed a change in physics of this particular one population at one particular scale, and while it's not necessary for all the rest, and just only see that is one particular Cepheid set, one particular sample, one particular scale, and one particular consequence only in H0. So it's rather particular, while the other explanation you take about dust is generality, which is acceptable from the point of view of physics and astrophysics, I should say. Yes. I mean, I just became aware of this paper you just presented, and thank you. And I will go deeper, but I think that, I mean, that's about the previous question, I could I think
that's a great framing. I appreciate that. Yeah, I'm just starting to process this also. But yes, right. Yeah, one seems more general, and this seems a very particular solution.
I will tell to Adam so to discuss with him on that. Thank you.
Yeah.
Okay. Other questions? No. So we can go to the discussion session now.